Thanks everyone. So I spent a bunch of time over the last 2 months or so learning about what's called zonal statistics, and so this is really has ended up becoming a quick summary of everything I've learned, and there are interesting challenges. And so part of this goal of this talk is to just like synthesize what I know, which is clearly incomplete, and see if anyone else is out there who's interested in thinking through some of these challenges and working on them. The stock is very different from what I thought it would be when I signed up for this. So it's going to be very rough. Some takeaways was, as I hope I will demonstrate, this was way too hard for me. It was the ecosystem is confusing. There's many different ways to do this particular computation, and they're all kind of special in their own way. And I think it points to the need for composable pieces, and that it is a fun problem to think about. So what is zonal statistics? Zonal stats is a GISE term. And for people who use X-array and pandas, it's basically group by. Uh, Specifically, it is grouped by a bunch of geometries. So that's where the vector geometries come in. And then usually the zonal statistic is that within a particular geometry, compute some kind of reduction, so some mean, standard deviation, etc. Questions you might answer with this kind of workflow is what is the average water table depth per US county? So a county is a shape, right, on a map. And so you want to aggregate some big raster field or some big array within those geometry boundaries. And there's a whole bunch of these geometries. Another question would be what area of the country is occupied by forests, et cetera, et cetera. I got introduced to this problem by like GIS people at NCAR. So I worked on this project called Flux, which was a way to scale up group bys. And the problem was how do you do a reduction over terabytes of data within like 4,000 US counties? And this ends up working pretty well, but that's basically an example of zonal statistics in one particular way. Zonal stats is interesting because it mixes the vector and raster worlds, right? So you have a bunch of geometries, but you also have these big arrays that can get quite big. And I think this is actually quite fundamental. Human infrastructure, in many ways, is expressed as geometries very nicely. And a lot of Earth system data, but not all, is really like these big array fields, right? And the output of the combo is usually nicely described by a vector data cube, which is this idea that you can have a raster array or like a little array, and one of the dimensions is indexed by a geometry. So in this particular example, these are populations indexed by polygons for US counties, I bet. Conceptually, there are two ways to do this. One is rasterize, or you burn in the geometries on the raster grid, which is like a fun term. But fundamentally, what this means is that a single pixel on your grid for your raster data can only belong to one geometry. And then there's ways you figure out which one, but that's basically it. And so once you do this, it becomes a standard group by reduction problem. You can also calculate exact kind of fractional overlaps of a pixel with a particular geometry. So here's a cool, complicated example from this very great project called Exact Extract. And then you might care about all these little details, in which case this is more akin to conservative regridding in the kind of weather climate space that I come from. And so usually you want to ask a question like, hey, get me the fractional areas per geometry for each pixel, group by a number of classification arrays, like what is a forest, what is a building, and then dot mean, right? So there's kind of two ways to do it, and it kind of splits up the ecosystem because a lot of people choose to do it either one way or the other way, and there's many wrappers for how to do each. There's a lot of complexities here. This is going to be super lightning. The grids can be quite fine. So at Earthmover, we've been working with lots of people, working with these global rasters or global arrays. So these are, covers the entire globe at a very fine resolution, usually something like 5 meter pixel spacing, 30 meter or 100 meter. Here's an example of a 30 meter array. It's like 2 terabytes and these like about 1 million points on each dimension, right? So these grids can get quite big, and so the data get quite big, and they're used to like composite data from satellites, for example. There's possibly a large number of geometries, so something like 5,000 US counties, 87,000 US watersheds. There's about 400,000 boundaries across all administrative boundary levels in this GADM data set. So, you can scale in many different ways. The dimensionality of geometries can be a problem. So geometries can vary in time, like glacier outlines or country boundaries or stuff like that. There's the dimensionality of grouping, because this is again fundamentally an array group by thing. So you can, I have an example here. I put it in the link. where some guy was trying to group over 6 different arrays, and they were all 30-meter global rasters. I will wrap up very quickly. And so the output of that thing looks something like this, right? So this is the reduced zonal statistic, and it's insane. It ends up being this huge, huge array, and it's kind of silly because it was formulated as a kind of multi-dimensional group by problem, and it was a bit wasteful, right? And so there was a solution to this that was kind of complex and involved like sparse arrays and this and that, and it was just a whole mess, right? And so just to kind of wrap up, this was kind of just too hard. This is clearly a very complicated problem. There's clearly a long tail of a lot of complexity, both on the raster side and the geometry side. And I didn't actually mention this at all, but like the existing tools that are out there don't actually handle this kind of giant chunked array without you having to build a lot of infrastructure. And so I put some links, and you can have my slides where I was trying to like think through this. And it seems like clearly we need composable pieces. And if someone's interested, please reach out. I'd be interested in talking about these things more and understanding how we can make a nice API, or at least pieces that can be used to make a nice API for this. Thank you.